Good afternoon. Welcome to your last session. Okay. Let's start with the last quiz. Now, according to universal approximation theorem, given enough capacity, we know that a feed-forward network with one layer is sufficient to represent any function. However, the layer must be massive and the network is prone to overfitting the data. Therefore, there's a common trend in the research community that network architecture needs to go deeper. This is something we covered in the last session as well. Now, deeper layers actually help us in achieving high receptive field. We discussed that part and we saw that if we increase the receptive field, what happens, right? We can actually start making templates for some of the objects, and that can allow us to match one object with multiple templates for us. We can break down our objects into smaller components. That is actually much more crucial for us. It is easier to train when compared to only one layer. Now, what also happens when we go deeper, especially in a resonant way or a let's say inception way where we have different connections, solving one parameter helps us solve the whole network. Every single parameter is linked to each other. Whereas if you're looking only at one layer, solving one there's no direct dependence of any other layer. If you just have one layer. It also helps us create large number of correlation templates for the same object, which is linked to the higher receptive field part. Okay, now receptive field of a network is 128, but the image is trained only on 32. What is going on? Large receptive field is making large templates with many orientation object variation for better correlation and convolution. Large receptive field is making templates which include background for the object as well. When you make your receptive field bigger, it will actually start learning about the backgrounds as well. That should be obvious as well. If our receptive field is very small, then we can only focus on the object part. If we actually have a much better receptive field, then we can start linking with the backgrounds as well.
But why do we care about background?
Because sometimes background is very deeply correlated with the object as well. For example, aircrafts will have very different, so 2 or 3 different kind of backgrounds. Either it's going to be on a runway or with some green patch, or it's going to be in the sky. That allows us to predict it much better. If you want to get a very convincing answer for that, then think about scene recognition. In scene recognition, you need background and you need objects also. We can't stop at object. We actually have to look at background over there.
It's not only it adds more parameters. Larger receptive field means more layers, means more parameters.
Okay, so you need to go back to this question then. However, one layer might be massive and the network would be prone to overfitting. So you're actually comparing one network with another network, same number of parameters, now you're going deeper. Now, if you add 16 identity layers to VG16, what will happen to the performance? Nothing. We discussed this last time. You can add infinite identity layers and nothing's still going to happen. It's going to just map the input to the output. So nothing is going to happen there. Now, does resonance suffer from checkerboard issue? Yes, it does. Anything which uses a stride of 2 will suffer from checkerboard issue. Now, we are talking about a kernel of size 3 and a stride of 2. We're not talking about kernel of size 2 and stride of 2. In that case, there is no repeating pixel, which is what max pooling is doing. So max pooling does not cause checkerboard issue. Now, if every kernel mapping in the Resident 50 architecture is multiplied by 0.5, what will happen? Now, the way we want to look at ResNet, is that that's the input coming in. We are going to convolve it twice, and then we are going to sum it here. What we are saying is that we are going to multiply this by 0.5. Right? Now, whenever such question comes in, you need to tell yourself that this is residue. Right? That's not really affecting our performance or not really changing the behavior of the identity part. Just for experimentation, your thought process, just for doing some thought experiments. This means that when X is coming in, you will be receiving 0.X. Right? And now let's say we add 10 such layers, which means that after this we are again going to add 2 convolution blocks acting as residuals, but again we are going to multiply R, whatever is coming in by 0.5. So this time it's going to be 0.25x. Now if we take 10 layers, essentially we are going to be doing this. So this is for 2, that is going to be for 10. So the more the number of layers, this number is going to get higher, which means this number is going to get even smaller, which means the overall data is actually going to just disappear if you just go deep with that. And that is going to cause vanishing gradient problem because the value is so small that the gradient is also going to be even smaller. So there's nothing to in fact change, right? Let's say we're talking about 10 is to minus 36 kind of value, and the gradient which is going to come back for that is going to change it in that region as well. That is going to be even smaller, and we even multiply that with a learning rate of 0.01. So overall value becomes even small. So we are going to get a vanishing gradient issue here.
Last point also is for this
lesser accurate network, then you mean then network actually trains, no training happens.
I mean, if you do like compare to standard,
You're going to get an NN for loss.
yeah, so yeah, exactly. So would you consider that lesser accurate?
NN for loss means you cannot train it, which means that accuracy is going to be, let's say you have 100 classes, 1%. So random number is going to be predicted.
In case of the previous question of checkerboard issue, the 3 stride of 2 is present in the residual layer, right? The identity mapping still goes through. So
Correct.
why will we have the checkerboard issue if only like residue has the like 3 2 and more the identity still?
Now, when we talk about identity, we are talking about identity because we want to make sure that we can understand the concept that because it's just a residue we're adding, we are going deeper. But if you're not doing convolution at all, then resonance should not work. So resonance does work. So skip connection is allowing us to just add more layers. So that 3x3 with a stride of 2 is important for us. It is capturing data and it is one of the bottlenecks through which the data has to flow. Right? In fact, we are doing 7x7 with a stride of 2 even before the network starts. So identity mapping actually starts after that. So you have already created checkerboard issue even before the resonant blocks are starting. Now, if all 3x3 stride 2 kernels in resonant architecture replaced by 3x3 stride followed by max pooling, do you think the accuracy will increase or reduce? It will increase, right? Now, what you also need to remember is that we are talking about a 3x3 with a stride of 2 replaced by a 3x3 with a stride of 1 and max pooling, right? Now, here, as we discussed last time, we are going to be covering some pixels 2 times and we are going to be covering some pixels 3 times. On average, I can say we are covering thrice each pixel, just to keep the discussion simple. Here, we are going to be covering each pixel 9 times. You are actually using 3 times more computation, and that is resulting in the higher accuracy. And of course, the checkerboard issue is also not there, right? So this is not sort of an equal comparison. If you have to actually equally compare them, what we have to say is that we are going to replace this by this in such a way that the computation budget of both of them are same. The computation budget of both of them are same, that means we are going to be using large number of kernels here. So let's say we have 32 kernels here and we have 32 kernels here and we want to compare them. We have to increase the computation budget of this 3 times. We're going to multiply this by 3. This is a very average rough calculation just to make sure that now we are comparing. Now both are apples to apples. We can't take some parameters and computation away from a network and then compare with another network. Now, if you compare which network is going to be better, this is going to be slightly better, like very slightly. That is why Resident prefers this mode, where the computation actually reduces a lot and they focus more on the kernel side later on, as compared to using a 3x3 with a stride of 1 and max pooling for the compression part. Right? Otherwise, you will think that why would you use a stride of 3, a stride of 2 if you are getting lesser performance? But you have compensated that by adding more number of kernels in your network. Okay, a robust minima will be more like a plateau than a spiky, right? We have discussed this part in the last session also. It will not necessarily be a global minima. There is no guarantee that there is a global minima. If a network has reached a global minima, that means there is no person in the whole world which can take the same network, apply a slightly better image augmentation strategy and get better result. You will never be able to get better result than global minima, but that we have never seen. And theoretically also, if you want to solve for global minima, you need to know something called the information entropy of the data set. And that is a good concept to understand qualitatively, but when you want to quantify that, that's very weird. Same face, maybe just for face recognition, it can be for face emotion also. It can be used for multiple different things as well. We are looking at a scene, or we're looking at a scene to identify a dog, or we're doing image segmentation, or we're doing instance segmentation. Based on the problem, the entropy also is going to be slightly different. Right? It's very difficult to calculate entropy for the data set we have. So there is a paper which says that we can find global minima, and like all mathematical paper, it starts with if we know the information entropy of the system, which means that if you actually have a tractable data set where you know the information entropy, it is guaranteed that you can get global minimum. Okay. We'll make the model generalize better to the unseen data, and that is actually what we are interested in. If our minima looks like this, that means the image must fall exactly here for us to predict the accuracy of, let's say, 95%. We don't like that. For an image which is not trained, which the network is not trained on, it's going to sit on the periphery where it's not going to be identified. But if we have this kind of minima, even though the accuracy is less, we have many images which can actually be identified. Okay, now which topology or loss topology is better, the left one or the right one?
Right.
It looks good,
Yeah.
right? But if you think from, in fact, mathematical point of view also, because it is smooth, we don't have a lot of crevices to get stuck at. We will be able to just slide through it, right? So parameter is not going to get many different confusion points. Right? Why don't you take a left? There also is a gradient. If you see on the left image, there are many gradients which might ask you to go in the wrong direction also. We don't want that. We want it to actually flow in a valley where you can actually get a better minimum. And whenever you add a residual connection or a skip connection or inception-like module, you're going to get graphs which look like on the right side. The left one is VGG, the right one is ResNet. There, the whole loss function is smooth because the gradient flow is actually much better. So solving one actually helps you solve more parameters as well in the equation.
Does Bashform also create smoother?
Batchman also creates smoother looking graphs, yes. Now, this is interesting, and we had slightly covered that, but not in the same language. Smaller datasets and architecture seems to require larger values of weight decay, whereas larger datasets and deeper architectures require smaller values of weight decay. Right? Now, when we are making this statement, we are saying to reach a particular value of convergence. To reach a particular value of convergence, we need to regularize the network. And as we discussed that if you are going to use two regularizations, you're going to reduce one of them because you're adding the other one. And what is happening right now is that the moment you increase your dataset or the moment you go for a deeper network, the value of regularizers you are going to use, like weight decay or dropout, must be reduced. Which means that when you're adding dataset, that acts as regularization. When you are actually using deeper networks also, that is also acting as regularization. And when we are talking about deeper here, we're talking about the connected networks like ResNet and Inception, right? So one hypothesis could be that the complex data provides its own regularization and other regularization should be reduced because overall regularization is something we need to make sure are not many. Whenever we are thinking about these problems, please try and think about the physical alternatives of this. The regularization is sort of dampening which we have. We want to make sure that our systems actually are moving smooth. If you had a lot of shock absorbers in your car, it won't move. The tire is just going to become rigid. You want to just provide exactly the enough spring force we need, and that is what we're sort of discussing here as well. It's cool? Okay. Now, regularization is the process of introducing small additional information. Essentially, what we're saying here is right. If we have just one data point, it is literally useless for us. We don't know where the gradients are going to be. If we have another data set, at least we can draw something on top of it. We know that the curve might be this, but there's still an approximation of what happens in between. The moment we add regularization, we are changing our data set slightly. Right? And the moment we change the data set slightly, we actually get many more points which can identify and help us figure out how these points might actually evolve. Then we can actually connect with a better approximating curve. Right? Now, a trivial example is that when we are trying to fit a simple linear regression, but you have only one point, we can't solve it. You have two equations and one point, we can't literally solve that as well. In this case, you can't estimate both the slopes and intercept. You need at least 2 points for that. So an estimate will be ill-formed if you are just using 1 point. If you provide some additional information, you can get much more reasonable estimate, right? That's what we're trying to do. A good example of this would be, let's say you're going to a particular city and you're asking for a house price of only one house there. And that house is $4 million. Let's say you want to buy that. And now you're saying that every house there is $4 million. Might not be true. That may be the most expensive house which is there, or maybe a mahal which was made by some king at that time. But every other house is, let's say, only 100,000 in that area. Now, using this concept definition and its extension, from below what all can be considered regularization. All of these are regularizations. Whenever you're using any one of them, you're changing your data slightly. All of them can be replaced by image augmentation. All of them can be replaced by the specific learning rate changes or Gaussian noise to your loss functions also. The reason we add all of these separately or we actually go for a combination is because finding the right image augmentation strategy for the network is very difficult. You really do not know that the data set which is there, and we don't process our test images also, right? We are not allowed to do our tests on validation data set and figure out most of the images are dark there, so I'm going to apply dark image augmentation on my data set. We apply multiple of these because one of them might be actually helping us solve a particular region as compared to what our intuition might be saying. Right? If your intuition is telling you something on your data set, it's probably wrong. Your intuition is built by looking at 100 images, 200 images, and the moment your finger gets tired of scrolling, your intuition has ended there. There may be another folder where the data looks very different. So unless you can see the whole data set, your intuition is still not going to be. And after seeing millions of images, your intuition itself is going to be confused. What exactly should we do? So rather we focus on multiple of these and test out which strategies and then test out which actually is helping. Now, if you're going for a dropout, L2, image augmentation, Gaussian noise, image augmentation is something you're going to do in the pre-part of the network. That is something you're going to keep it consistent. Today, we're going to discuss one strategy which should become your by default strategy for every single data set you're going to look at, except for the object detection. There we have to do slightly different stuff. So let's take that out, that part out. Small Gaussian noise to the loss function is something similar to what you're doing in the layers as well. When you're doing batch normalization, we have actually done that part there. So let's take that part also. Large learning rate, we are going to cover this part today. So what is left out is dropout and weight decay. And let's say you have some other ideas of doing regularizations also. You should try to use one of the three and then test your network for some time and then see which one is actually giving you better performance and use that in the majority and then use the rest of the other guys in a small numbers. You have to basically test your models, right? I like to say this to people. Your days of using default parameters in a network is over. Your days of downloading CIFAR 10, connecting to a model, giving a SGD of 0.01 learning rate and click model.fit is over. Now the difficult part of machine learning is starting for you, and that is the hyperparameter search. How do you find the right parameter to train the network? Because if you just want to train a model to 80% accuracy, you have done that in assignments many times now. But now the target is how do we take one model and push it to extreme? How do we take that model to predict 94%? And this is something we're going to see today. Alright, any question on the quiz?
How we implement this one, this small Gaussian noise loss function?
I'm going to cover this part today also. Okay, now today's session is on advanced concept and superconvergence, and as I shared last time, I've added a video so you don't have to scroll and then look at the video. Okay. Now, learning rate is one of the hyperparameters which is going to be extremely crucial to you. Till now, you just kept it constant, and in fact, in the I think code 7 we added our LR changer. So as you're training a model, you're changing LR also, and we have some intuition of why we need to change learning rate. As we are training debug, we want to fix the LSBs now. We have fixed the MSBs, our most significant bits. So 0.0345, let's say 34 is important for us. So we fix that using our big learning rate. The moment you now need to fix the smaller ones, you have to go pick a smaller learning rate and then start fixing them. And let's first look at this particular chart. Okay, now this is the input image which is flowing through our network. We are using some kernels here. We are going to convolve on top. The moment we convolve on the channels coming in, 3 channels are coming in, we have done our transformations here. So this process is called data transformation. It can be many different things. Batch normalization is also data transformation. Adding ReLU is also data transformation. Whatever changing our data is data transformation. So this is the layer 1, layer 2, and finally we are predicting what we want to predict. And let's say we are doing simple cat versus dog. Right? Now image goes in, we say it's a dog, but the label actually was cat. Right? And now we actually don't predict dog, we are going to predict 2 numbers. Or let's say we are using here let's say single number only. So 0 for cat and 1 for dog. That is what we wanted to predict. Now we are predicting dog, but we are going to be predicting some number there. We are going to be predicting that I'm seeing 80% features of the dogs here. But this was supposed to be a cat. So our loss is going to be 0.8 minus 0 whole square. It's a big loss which is flowing in. If we were actually using, let's say, binary, not binary, but cross entropy here, so which means we have 2 numbers to predict. So the output would be 2 here, right? 1 digit here and 1 digit here. This is for the dog and this is for the cat. We wanted to predict 0, 1. We are predicting right now 0.8 and 0.2. In this case also, we would be doing 0.2 minus 1 whole square. Right? This number needs to be larger for this number for the whole loss to be there. We need to calculate for dog and we need to calculate for cat. Same thing is going to come here. 0.8 minus 0 whole square and 0.2 minus 1 whole square. That's the loss which we are going to calculate. Is the part clear? Okay. That is only one image going in, but we know that we use a batch size of 32, 64, 128 or some number of such order, right? That means I'm going to pick an easy number. That means 100 images are going in, right? And I'm going to check this loss value for every single image I have. I need to look at the average loss right now. On average, how good I am. In one cricket match, Kohli can also get out on 0. Right? That should not define the network. So we're going to test our network for many different samples, and then we're going to average the loss, which means I'm going to accumulate all the loss I have for all the images. Let's say X goes from I to 100, right? And that this is Li for that particular image, and I'm also going to be dividing by 100 to make sure I'm looking at the average loss here. Is that clear? Okay. Now let us consider one specific kernel here, the last layer, and that kernel is going to be some 3 cross 3 cross 512 for us, right? So this is 3 cross 3 cross 512 for us. I'm only interested in this particular one weight here. Is it clear? Just that weight. Okay. Now it is receiving 512 channels from the last layer, correct? And this weight is going to convolve on this channel and it's going to give out some value. Okay. So let's say the weight initially was 0.3. Cool. Okay. Now because it is giving weight, the weight is multiplied with the channel value coming in, and we would have done gap and so on. Finally, this weight's contribution is already taken care of by the overall network, and I'm predicting a particular value for the dog right now, and the value for the dog was 0.8. It's cool. Okay, now let us assume that this particular kernel was an important kernel for the dog class. If this kernel is an important kernel for the dog class, if this value reduces, let's say it becomes 0.2, right now I'm predicting dog, I should have predicted cat, right? And okay, right now I'm predicting dog, I'm predicting cat, but let's say this is important for the cat. We are more interested in getting the right value here. This kernel is important for the cat. Now if this value from 0.3 becomes 0.2, the cat which was being predicted at 0.2 will also drop. Yes, no? If the kernel was important to predict the cat and I reduce the value of the kernel, and I'm hoping there's a positive correlation, I was predicting some cat body or cat nose there. If I change that particular kernel, the value of the cat which I'm predicting right now, already very bad, it's going to go even bad now, even bad, right? Which means that if I, on the bottom, the new one minus the old one, this is what I'm writing, this is the new value which is there, this is the old value which is there, and on top we are looking at old value becoming even smaller. Is that clear? Right? I'm going to add a negative in front of this just to see what exactly happens now. Now, what have I done for the weight? Have I reduced it or increased it? Reduced it. What happens to the loss? Accuracy, let's say.
Accuracy.
Right? Or my
Loss increases, accuracy reduces.
Right? My loss also is reducing right now. Loss also is increasing right now. Right, it is 1 minus 0.85. That is what I should be looking at. I'm writing 0.2 here. I should be looking at 1 minus 0.85. So let me write that because that needs to make much more sense. 1 minus 0.2 whole square, and now it is 1 minus 0.18 whole square. And this is what I should write. Right? Now this is more and this is less, which means on top I have a positive value. On bottom I have a negative value. Positive divided by negative is negative, and we have negative in front, right? So that becomes positive. Now this positive means that I need to actually increase the value here. I don't need to reduce it. I need to do opposite of what I'm doing right now. Right? Now this is some value which is coming in, right? A positive value, and let's say this positive value after calculating is 0.1. The way we update a parameter is we say that Wt plus 1, the value which I have to update right now, is equals to Wt, the value at which I was right now, minus this equation. Right? That's the whole equation we're looking at. We are looking at theta t plus 1 equal to theta t. Theta is weight minus delta L on top and delta theta on the bottom. So what right now is happening is a positive value coming out automatically, which means my theta t, whatever it was, is actually going to increase because I was reducing last step, and that's a scheme of things I'm seeing. Now let's change this.
How do you know what is the loss that you're doing? The 0.18 is the loss that you're expecting next.
How do you know we are at point 2?
Point 2 is what we have, right?
How do we
That's
have that?
assumption, that's assumption, right? I mean,
No, yeah, but
by
how
reducing the weightage of
no. Hold on. We know this is 0.2 because the prediction right now it says 0.2, right? Prediction. I'm going to make a very simple model. Last layer for me is a 5 cross 5 cross 512. I'm doing a gap on top, right? After doing the gap, I get 512 numbers. I'm going to use a 1 cross 1 cross 512 cross 2. This gives me two numbers, one for the dog and one for the cat, right? This is 0.2. This is not loss. Loss is 1 minus 0.2. Right? That I'm focusing on this value right now. And that value is coming from this gap. And this gap is coming from this guy. And this guy is coming from a 3 cross 512 kernel. Let's say 512 here also. Right? I'm focusing on one of the parameter here. And saying that parameter was important for the cat. You have reduced that parameter, which means this value for the cat is further going to reduce, which is a bad thing. Clear? Okay, now let's do the reverse of this.
Last equation is WT is equal to WT plus.
Which one?
WT plus 1 is equal to WT.
I'm going to write it again. Right? Now let's do it again. The equation is WT plus 1 or theta T plus 1, same thing, equals to WT equals to theta T minus L2 minus L1 divided by W2 minus W1. Sorry?
Okay, so minus okay.
Okay, and same for theta T, same equation. We may use. Okay, now this is the old value, same as this value. This is T and T plus 1. Right? Now instead of reducing this, we increase this. If we increase this, this is more than this. So on the bottom I have a positive. And what is going to happen on top? Earlier the loss was high. Now the loss is going to be low. Right? So on top I have a negative now. Negative divided by positive is negative. Negative and negative is positive. So a positive value gets added there, which is what I want. I want to make it even bigger. Right? I've just increased my weight. Okay, let's pick some values. This is 0.3. So I have on bottom 0.3. I'm converting this into 0.4. Right? This is a gradient we are checking right now. We are calculating right now. We don't know what to add. Right? We're just checking. It's a positive value which I need to add, a negative value we need to add. This is just a check. Now on the bottom I have positive value. Now when I was using 0.3, my loss was 1 minus 0.2 whole square. If I'm using 0.4, my loss becomes 0.22 whole square. This is a bigger number than that number. So bigger number minus smaller number is going to give me, this is a smaller number compared to this number, right? This is smaller number, right? My loss has reduced, which means on top I will have a negative value. So negative divided by positive is negative. Outside I have negative. So negative and negative becomes positive, which means whatever I'm calculating here gets added now.
Then the last amount is getting added when you reduced, right?
Yes, because I was reducing.
So,
In the last example, I was reducing and it was
positive.
what getting added? What does it mean? I should add. Now when I'm adding, it is still telling me add more.
Till what point you will go?
Till I actually get to some specific value where the loss starts increasing. Right? Now this is the kernel we are talking about. Right? Now the kernel can increase to some specific value. Right now let's say the kernel is at 1.3 and that is where it should be. This is where it's giving us the best result. Now the last value was asking me to increase it. Now let's say we increase this to 1.4. Right? So on bottom I have this positive value now. On the bottom I have this positive value now. My loss was completely 0, 1 minus 1. But now my loss is increasing, which means the prediction is reducing, which means I'll be doing 1 minus 0.9. So on top it becomes positive. So I have this positive now. Right? Okay, so that's how we're going to play around with our loss function. And okay, comment on this. I possibly shared this with you earlier also. Now, have I shared this with you? The jet analogy? Yes. Right? Okay. Now, this is a snapshot of a loss function taken at a specific point. This is how the gradient related to a loss function. But that's not what is happening. We know that it has to travel, and if it's going to travel, we have to target that part also. Okay. Now, this is the gradient update we just saw, right? I did not write alpha there. Alpha is the learning rate which is going to multiply with the gradient we are calculating. And alpha is what we're going to be focusing on today. And that is something we need to make sure is going to be adjusting the number, the bit which we want to fix for the variable. If it is 0.0456, we have achieved 456, we are now achieving the next bit which has to be fixed, and that only can be helped by our alpha. Okay. Now, mathematically, gradient is a partial derivative of the loss function with respect to the weight. We discussed this part also. I have 3 cross 3 cross 512 as one of the kernel which is there. Not only all the, except one, all the other weights here, but all the weights of all the kernels are going to be considered constant when I'm calculating the gradient for this particular weight. I'm not going to update my weight. I'm still going to use my old weight to calculate W2 now. I'm going to keep constant W1, W2, W3 and calculate W4. Everyone is going to be considered constant there because we are doing partial derivatives here. And logic we are using mathematically as well that the gradient is so small, the change is so small that it should not affect the loss function. These are the approximation we have to use to make sure that we can actually do partial derivatives here. Okay, now there are top 3 optimizers. This equation you're seeing right now is the gradient descent equation. Right? There are multiple optimizers which exists out there, and these are the top 3 which you're going to hear about. One is called gradient descent, then we have AdaGrad, we have Adam, we have AdaBoost, we have AdaDelta, we have Eve, we have RMS prop, and many more. Right? The one we are going to focus on is called gradient descent. Now, a perfect gradient descent means I'm going to look at every single image in my data set, do one forward prop for every single image I have, and then do one back prop. That is called actual gradient descent step. But we don't have a GPU which can actually do that on a batch size, so maybe I have to do it again and again. Finish 100 images, wait, finish 100 images, wait, finish. So I'll have to, it's going to take a lot of time. So instead what we do something called stochastic gradient descent. Now stochastic means one image at a time, which means only one image is going to go forward. I'm going to process that, take a back prop step, then one image forward, then a back prop step. Which means when you're writing SGD in your code, you're not doing SGD because you're seeing a batch of 32 also. Is that clear? So don't fight with an academician telling him that you are running SGD. You're not running SGD. What you're running is called mini batch gradient descent, where we mix both the worlds. I can't take a look at my whole data set. I can't do back prop for one image only. So I look at a batch of images, and then we are doing mini batch gradient descent. So technically we should call it mini batch gradient descent, but there are too many words we have to use. We just call it SGD. We're too lazy for that.
Mini batch gradient descent, all the images go through one forward and then come back.
Yeah, that's the best possible step. But you need a cool GPU for that.
Right now, when we are taking batches and running, so that time it takes a batch of images and it will extract all the kernels of that batch. And again, next batch again, those kernels will be there, new platform.
Then you update with one.
They are updated.
After the batch, we do back prop, which means all the kernels are updated. So new batch, new set of weights, new set of nudged weights. These are all weights only, but slightly nudged in the direction we are looking at.
And when we test that model, so that will be like one image at a time or all the images at a time?
No, your model is trained for batch. So even when we are testing, we have to fake that we are sending one image. We have to say that. So your model is expecting a batch in a folder, set of images in a folder. So when we test it and you send one image, it's going to say, I don't recognize this. I need a folder. So you have to do something called dimension expansion, something you saw in the code for the VGG in the last session also. So you're going to fake as if one image is actually not one image, but multiple, but others are missing. So we fake a batch and then we send that. A batch can have any number. So when you're using
a batch of one, then
sorry,
you make a batch of
you're taking a batch of
image.
one. Yes. But see, it's like contradictory, a batch of one, but we have to use it because the numbers are like that. It's cool. Okay. Now we're going to focus on gradient descent. We are SGD mostly. We're not going to focus on Adam and AdaGrad. I'm going to share why we are not going to do that. Now,
So, when we find a local minima, how does the global minima and local minima relate? Do we need to have any relation between a global minima and local?
global minima is a dream where every model wants to be at. Local minima is a reality. So Instagram versus reality, same thing. So global minima is that factual space where the model can be. And what I believe is that global minima does not exist, because if you have to just map it with a green, right? My network right now is able to recognize 1,000 objects. right? And Russian scientists have just made a new dog. It's still a dog. Or let's say, let's keep it simple, because there are 100 classes of dogs, so you can say that classes of dogs is a new class of dog I'm adding. Cars is one single class. It is trained on the cars. Now Elon Musk has launched that Cybertruck. Now that also has to be recognized as a truck, not as a car. It looks like a car, but it's a truck. So now there is no end to the greed. Certainly the data set is increased. So it's a non-solvable problem, which is always going to be difficult for us to figure out. And it's not for the model also, it is for us also, right? You have seen maybe 10, 20 different kinds of dogs. You can recognize that that's which kind of dog it is, or it may not be similar, but you'll not be able to take a name for what that dog is. And I can show you Mini Cooper and Mini Cooper S, and you from normal eyes will not be able to figure out what is the difference between Mini Cooper and Mini Cooper S. You really have to be an expert in that domain to say, okay, that's the actual difference. So when humans, so we have 85% accuracy on ImageNet. AI is at 87%. Right, so we can already see that it is already succeeding in things, and this is with 15% wrong labels in a data set. ImageNet, which you hear of, has 15% wrong labels, and then AI has a accuracy of 87%, which means it has figured out the wrong labels as well, but correctly predicting in the actual data set. You see how close this is? You cannot get a model better than this now. But again, it's a dream. A new code is going to come next month. It's going to say we have beaten 87% also. Clear? Okay. Now, stochastic gradient descent. As I shared with you, stochastic gradient descent is only for one image. We can't do this. We can't do multiple iterations or millions of iterations just to go through our data set. So we are going to pick a batch, and that is going to help us process the things faster. Now, what you're seeing right now is a loss function, which is a function of our images, which are x, y, which is our label, and theta, which is our parameters. Right? We can use W or theta for today's session, but don't get confused. Both are the same things. But when we calculate a loss, we are interested in the average loss. We are going to look at all the images we have in a batch, and we are going to divide that by n, and n happens to be a batch size. We are trying to look at the overall accuracy of the model. Okay, now this is vanilla SGD without any frills. It's the simplest SGD you're looking at. Here, this is called a grad function, the upside down triangle. Here we are taking a gradient of the loss function with respect to the weight, right? And that's the value with which we want to actually backpropagate. The idea here is this is a loss function, let's say, and this is the L theta right now, right? The gradient there and the gradient here, right? There are the tangents there, and they tell us that how much should I move in that space, and I need to move smaller as I'm proceeding. So I'm going to take, let's say, this gap, and that's the triangle I'm interested in. So I'm going to move this bit only. But as I take a gradient here, the same gap is also going to be taken, but for the lesser loss, because the angle is also reducing. That gives me the angle, and that pushes me in the direction because of the negative sign. Alpha is something which we have to measure here. Alpha is something which you have to maintain. Let us say this is 0.003 and this is also 0.003. The gradient delta you're checking it for. But we can't move same steps. If you move same step, it's going to be a nightmare for you. For example, let us say that you get a boon from a genie that you can only move 5 feet. Right? Now, then you cannot go out of the room today. You can only walk for 5 feet, no less, no more. You're in front of your house door, which is 1 feet away from you. You're going to go 4 feet ahead. You're going to come back 5 feet. That's a shuffle which is going to happen. We don't want that. So we want to reduce this 0.03 to a smaller number. That is where this alpha is going to help us do that. Quite clear? But it is still a normal SGD. There's nothing which we've added here. Now, this is what we hope we are doing. Those angles or those directions are allowing us to go in the right specific direction. That is what we are hoping that it is. That is what is happening right now. Is it quite clear? But it's a hope. There's still some issues which we have to juggle around. Okay, and you can also see that I'm not going in a straight direction here. Right? And you cannot go in a straight direction. Why can't you go in a straight direction? There's no straight road. It is going to go through some valleys and other systems also, right? There's no straight road. In this diagram, maybe you can see a straighter road, but there is no straight road. And we are talking about 1024 dimensions collapsed to two dimensions. There it might look simple. But 1024 dimension, there are many other dimensions where they might be actually doing something bad to our network. Now, this is one thing which I will try to explain to you, but if you're not able to understand that, then skip it. Right? It's not important that you really get this concept, but it's good that if you do. I'm going to use some numbers intentionally. Let us say there's a tug of war between 60% of the variables and 40% of the variables for a loss to be a particular value. If you move up your particular parameter, I'm going to take, in fact, a simple example here. Let us say, unfortunately, this particular variable, theta, right now is confused, which means it is not clear that this is actually working for the dog and it is working for the cat. And that is going to happen. We have just initialized the network. All the kernels are going to be confused. It has to take a side eventually. But that is where our parameter right now is, right? Now, let us say it is helping dog get a value of 0.5 and is helping cat get a value of 0.5. Cool? The moment I change this value to, let's say, in this direction, the moment I increase the value or reduce the value of this particular guy, dog becomes 0.6 and cat becomes 0.4. Next iteration, it has to come back to this particular value to make sure that it is reducing the loss for the cat also. So there are going to be some points in your network or some positions in your network where variables are really confused in what direction they need to go. The moment they decide to go in a specific direction, they end up unfixing something, right? And that kind of point is called a saddle point. Is it part clear? Okay. Now there's another issue which may happen in a network, and that is called a plateau, where your point gets stuck somewhere here. Now here your gradient of theta of your loss theta dash is equal to 0. It's just stuck there. Doesn't matter what you try, whenever you calculate gradient, it's just there. It's not able to move. Is this part clear? Now, how can
training part? Are we talking about training part? When we train with specific dog image or cat image. In fact, we don't put two animals into the same thing and train. Isn't it?
Correct.
So then, if we are talking about training part, we always move towards identifying the dog image. Right? Let's say we are training the dog.
Image of a dog is coming in. What should the parameter predict?
It should go towards dog itself.
But it is predicting cat also right now.
Yes, but when you are trying to reduce the loss function and when you are trying to find the weights for the next step, you will move towards dog.
Okay.
And you said that at initial.
That is what I'm saying. That you need some imagination to comprehend this part. This is the variable we are talking about. This variable works with this guy who works for the dog. This variable works for this guy who works for the cat. Right? Right now, is it getting 0.5 from this guy? Is getting 0.5 for this guy. Dog image of a dog came in, and I'm testing for the dog perfectly fine. And according to that guy, you have moved it in this direction, so now you're getting 0.6 here. I have not checked my cat right now. Next image of cat comes in, it's going to check this variable and saying, dude, you're giving me 0.5, now you're giving me 0.4, and that is not allowing me to predict my cat better. Please go back to cat 0.5. So it goes back here again. Next image of dog comes in, it's going to go back here again. Next image of dog comes in, it's going to go back here again. Right? Every single parameter is in a chain of commands of some links, and you have to look in a overall perspective. What you're saying is correct. That happens also, but this also happens also, and this happens in the early part of network. Later on, everyone's taken a decision. For example, if you are 25, you're already taken a decision. You're Congress or BJP or neither. So as we train a network, you get more information to take sides with. So maybe luckily cat images won't come for some time. There are 4 images of dog. I've moved so far away from my cat that I'll not go back. That is also possible. But these situations do arise. And they used to be a problem for us, but they're not a problem for us anymore. But you need to understand this from understanding why we are doing some of the things we are doing. Another problem, so this is called saddle. And this is called plateau. In plateau, the gradient does not exist. In both the scenarios, right? In the saddle scenario, I can't draw saddle, but let's say. Yeah, I can draw saddle. Okay, let me draw saddle. Yeah. So the magic? Okay, now in this scenario and in this scenario, what do you think we can do? How do you think we can fix this? Think physically, don't think from program point of view. Imagine that saddle point physically is actually, there should be some reason it's called a saddle point, right? And saddle point is that it looks like saddle, which means that the moment you try and go out, it comes back to the same point. And that's how the horse saddle is. On the where you sit is actually some depression there, and then you have fall. You want to go at that particular fall, but you're stuck there. You're stuck in that small depression. Wherever you go, it just pushes back. So if a ball is stuck on a saddle, how can the ball come out?
Use more force or more weight.
What is the answer? Push up. No, we can't push the loss function, right? Loss function is there. We can do some change to loss function, but we can do some change directly to the ball also. You can just flick the ball. You can just apply some force to the ball. The moment we apply some force to the ball, it is going to go in either this direction or that direction. It's safe. This ball is going to go in this direction as long as the momentum allows it to go. So that's the key word, momentum. Now we don't know when we need to go to a model, to a particular parameter and click it. Imagine a network where it gets stuck and you have to go and click all the variables for it to get pushed. And there are millions of the parameters for each patch. So each patch you have to go back and click again, force goes. It's a very dangerous scenario for us. We don't want that. So we are going to say that we have some momentum. What if the molecule actually had this momentum? When this guy actually fell from here, it was carrying a momentum. Now, if momentum is there, even if the surface is flat, it is going to continue moving. Part clear? 100% clear? Okay. Another thing we can do is that we can actually change the loss function slightly. One is we directly work with the parameter and add some momentum so it carries forward. But let's forget we don't have momentum. Let's say we don't have momentum. Another thing we can do is to just change this slightly. I've changed the loss function slightly, and we know how we do that. We add, let's say, dropout, we add some different image augmentation, and so something is done there. The moment we do that, I'm going to get some gradient, maybe in the wrong direction also. It doesn't matter. We just want to shake it. Right? You do it multiple times, it is going to figure out that I need to go in the other direction. So the moment we do this, we have this angle available, and the ball is going to roll in the opposite direction, which is the wrong direction right now, by the way. And we don't know its correct direction, but we just want to keep shaking it to make sure that it figures out what is the right direction. Right? And you're seeing 2D right now, right? Maybe in 3D it looks like that. So the straight line, if it's going here, but maybe at the front it has some depression to go somewhere else also. And this is 1024 dimension. We can't extend our imagination there as well. Is this part clear? So we can fix this by small gradient. Now look at this equation. This was there in the quiz. Someone had asked that part. This is the theta we are trying to update. That's the theta I have. That's a learning rate which we discussed. That's a gradient which we're calculating. We're adding small noise to it. This noise is literally picked from a random distribution of Gaussian. It's a Gaussian noise essentially. We pick some small value from there and just add it back to our loss function. So your loss calculation is noisy, which means you can never get a flat, or you can get never stuck in a. But now you know you're changing a loss function also. Sometimes that's not a cool idea. Small gradient is still fine, but if this becomes a nightmare for you and you keep on adding a big value, it may not be a cool idea. Maybe the gradient itself has become so small that you are right now looking at this kind of value. But the noise you're picking right now is maybe this. You see the gap? So dangerous to play with, right? So you have to modify that also as you're training further. Hopefully our alpha will be able to manage some of this part, but again, still very dangerous to play around. Okay. And this is how we add.
Can you go back? Just to the equation. So we can ideally add noise to learning rates. What I mean to add to the function.
Repeat that.
You can just add a noise to learning rate. Probably you can make the learning rate as
This already exists. When you add noise to learning rate, you are talking about another system, which can also exist. So this thing already exists. Someone designed it. Now here we are looking at Gaussian noise, and that's how you can add a Gaussian noise to a layer. Here we are adding to our loss function. You can add Gaussian noise to a layer also. Right? There's a bit of noise added.
Is there any particular reason why we have got
Gaussian noise is always close to 0. So most of the values are going to be very small, and we are picking up sigma there, which is going to the standard deviation basically, which is going to like an electron cloud. Many more molecules, many more times available there, but it disappears as you go down, go into its outer periphery. So the risk of you picking a larger value is very low when you're picking Gaussian noise, as compared to a random distribution of numbers.
How do we determine where to add Gaussian?
Right now we are adding to our weight, and the way we can add to our weight is by adding to our layer.
Actually, writing on the batch update, whenever we are doing the batch update, so we are calculating the del L part. So we can calculate, okay, for particular partial derivative of L, if it's like less than a certain number and it's for like certain number of epochs, we can add the Gaussian noise there itself and just modify that.
Yeah, so as long as you have to do something manually, that seems like an approach which is going to take a lot of your time, a lot of your tests to figure out those values. That is exactly how we used to do things early on, and that's called hyperparameter search or a grid search. But we are trying to avoid as much grid search as possible. There are many other parameters which we need to take care of. And if you add this also, then...
So whenever we are adding this Gaussian noise in the layer itself, then we are essentially adding some regulation technique or some like forceful noise. So it's
Correct.
not able to learn the exact meaning or exact gradient.
That's why the signal has to be very small. So it's a very small noise which we add.
Just a nudge.
Just a nudge. This used to happen, but you have not seen any network which is using it. So I'm basically taking it to the concept which people are using now. But that is possible. If you want, you can use this, but not use anymore. Why? We have a dropout now. We have cut out now. We have much better strategies than adding this noise, which we have to figure out what sigma should be for each layer. So that's what we're trying to do. We're trying to simplify the whole thing. Now, if you are actually using, let's say, cutout directly, you may not even have to use dropout for regularization. That is what I'm saying. I would say that we indirectly already doing this. We are doing this indirectly by dropout. When you do dropout, some of the pixels are dropped, which means the next layer is already going to get some sort of noisy input. Okay. Now comes the momentum part. The same stuff which we discussed. Okay, so our older equation was right, that's the old equation. What we have done is we have moved this part here, right, and we have moved this guy here. Right, that's what we have done. Now let's see that what actually is happening when we are doing such a thing. Okay, now let's start with t equal to 0. This v is called momentum. Right, it's called momentum. Now when time is equal to 0, there is no momentum there. The model has just started, which means our vt equal to 0. There's nothing which we are adding, which means that's the only term which we are going to calculate. That comes here and that comes here. Same equation, no change. All right. So our Vt at that time was, I'm writing t, not t plus 1, right? This is t plus 1, let's say t plus 1 to keep it easy. And the rest of the stuff which I have. Okay. Now let's say our t is equals to 1, which means this is t equal to 2, and that means this is t plus 1. This t plus 1 is the last direction I had gone in. That's the last gradient which came to me. I'm now calculating the new gradient. That minus is part of that guy, right? I'm now calculating new gradient. And I'm multiplying this by mu. Please consider mu equal to 1 for next 5 minutes. So mu is not there. So I'm looking at the last gradient and I'm adding the new gradient to it, and that is what is getting added here. Is it part clear? Okay. Now this gradient right now can be considered as L2 minus L1 divided by theta 2 minus theta 1, right? Can we consider this as speed? Just for discussion. There's something divided by something, distance divided by time, some of that order, some sort of speed in that order, right? Now, which means this is a vector. Let's say this is actually velocity, right? This is a vector. For a short duration, this is actually a vector. So that's the vector which is there. And this is another vector, which is the old vector which I have. That's the vector I have right now. Now, when we add two vectors, what happens? You're going to get the combined vector. That is what is happening here. Now, why this is working is, now imagine that bear with me for some time. I really want you to believe that this is an aircraft carrier. Let me make an airplane also, just in case. Looking opposite, it should be looking at the direction. Okay. Now this is a turret, and on top of turret we have this tank, which is going to shoot our aircraft. Now that's the aircraft we have right now, which is flying in this specific direction. Right? Now, if you're a soldier there, you're going to see that the aircraft is there. You're going to do some calculations still. You're going to imagine that that's going to come here, and you're going to shoot it, assuming that it's going to reach that point, and then you have shot this, right? So your missile is going to go in this direction. Your aircraft is going to go in this direction, right? Your aircraft is also a smart guy, right? He's going to get some idea of where you're trying to shoot, and or manually start changing direction just to make sure that you cannot get an accurate shot. Your old shot is already left. It's gone now, useless, right? So this way you will never be able to kill an aircraft unless the aircraft is directly coming at you and you're seeing that movie where you're shooting. It's a Pearl Harbor. The aircraft has decided to come directly in your direction. Then you're lucky or unlucky. Maybe it's dropping a bomb also. So that's not going to work for us. But let's say we have this missile launcher. So from there we are going to shoot this missile. And that missile is going to actually target this guy through the heat signature. Now, earlier we were doing simple update. When we were just doing this theta t plus 1 plus at delta t, you were actually seeing that is where it should be. I'm just going to shoot it. But now what you have done, this aircraft is going to see that you are here now. That when this missile is reaching at this specific point, this aircraft has reached this specific point. So this was the old velocity. This is the new velocity. Based on that, it's going to figure out, okay, that it should actually shoot here. Is that clear? That is exactly what we have done in this equation. We have added the last velocity of our change, the current velocity of the change, to know the combined velocity in which I should target. That's where the momentum part comes in. And it of course helps us to go out from the plateau or get out from the starting point also. Is the part clear? Okay.
In the saddle point, if we are just considering only 2 dimension or let's say 1 dimension, and the point is in the middle, so we are adding some velocity here, saying okay, it should go here. It will keep on oscillating in that point itself.
No. The last momentum is what you're adding, right? If you reach, let's say this is a saddle point, and you reach the center, you're coming from this direction, that means that momentum is still there, it's going to take you up. But and there is a chance that after you go up, there's a down.
The velocity will keep on decreasing as it moves up.
As of now, no, because it's momentum which you've added. There's nothing which keeps on reducing. Because the gradient will reduce. Because the gradient will reduce, but last momentum is still going to carry to some level. What you can say, my value is such that the momentum is useless there. Perfectly fine. I borrowed that point, but maybe the value is small and I can actually get out. That's what we're discussing. Is part clear? Okay. Now. So okay, this is a momentum for us where we are taking last momentum and trying to make sure that we can actually adjust our points as we move. But we have something called Nesterov also. Nesterov is an update to this momentum, right? What Nesterov does is, it divides our equation into few more parts. what is happening right now is this equation remains same, right? That equation remains same for us, has not changed. Vt plus 1 is equals to mu Vt, same mu Vt had, and this alpha gradient theta, the same alpha gradient theta we had, but this theta had changed. This theta was theta normal t for us, but now this is t plus 1. Now t plus 1 is what? T plus 1 is a new theta, which we have already calculated using the last momentum. So what this is doing right now, it's saying that I have that momentum. I'm going to calculate my new position. From that position, I'm going to again observe my aircraft, where exactly it's moving. And then I'm going to predict that at that location, I should actually go in that direction. So I am calculating ahead. So I'm calculating 2 steps ahead. First step I've already done by momentum. Second step I'm actually doing what? Okay. Rate of change of distance is speed. Rate of change of speed is
Acceleration.
that is what we're doing similarly here. We are actually calculating the rate of change of acceleration of the aircraft now. So if it's keep on moving, I know it will continue to move. So I can actually calculate for the 2 steps ahead and hit it there. So it's yet slightly more accurate. So that's where the Nesterov momentum comes in. Is the part clear? When Nesterov momentum came in, people went mad.
This should be used.
No, not for that. Oh, you can get this complicated, we are going to complicate it further. So what another algorithm is doing, it is saying that this loss you are calculating right now is for this theta. The loss will also have momentum. Loss can also have momentum. I'm a missile, I have my own momentum, I'm carrying that. But the loss will also have its own momentum. The aircraft will also have its momentum. What if we can calculate the momentum of the aircraft and then use that in the equation? That is RMS prop. So RMS prop, Adam, Ada delta, the variants of these guys slightly different, but they are making this further more complicated. And there's a reason why we are not going to go inside those optimizers. Is the part clear? Nesterov is clear? Okay. So the question is which one to use. Now look at this graph and tell me which one do you think you should use.
The ping.
See, SGD, it is still not calm, it's still traveling. And the momentum, the green guy, the last guy to approach, and it is overshooting also. Right? There's another graph which is there. SGD is just stuck there. Momentum somehow makes a space and come out. Right? When I'm asking you a question, which one you should buy, I'm actually doing this to you. Which phone should you buy? These images, which you will find online, are not designed by HDD guys, they are designed by these guys who want to show that HDD is a useless system, which does not work. Right? These are ads. Your loss function will never look like that. I told you, loss function is not going to be a stable point from where you are going to arrive at. This is a specific function they have wrote, and there are animations which are showing you that how LCD bad can be. Is it clear? These are manipulated results. Why I'm saying that? I'm saying that with confidence because these are the actual results. In this result, we're comparing HGD. HB is hybrid HGD, which is HGD plus momentum. We have Adagrad, we have RMS prop, we have Adam default, and the new Adam added delta, maybe some variant. There you see what is happening. Look at the black and the red lines. This is your training error. This is your test error. If you're not convinced still, then ResNet, DenseNet, ResNext, SCNet, NASNet, which is the state-of-art network right now, ENAS, EfficientNet, MobileNet V1, V2, Exception, Inception V2, Inception V3, not Inception V2, Inception V2 tried to use something else. Why everyone, including VGT and AlexNet, the guy which actually started the program which started the whole machine learning, is using SGD with momentum. You get the point? Now, if you go and search online and try and search which one is better, people will have their opinion. But if you listen to guys like Leslie Smith, who actually have done some last 30 or 40 year of work, they are going to tell you that no one knows why these guys work. No one knows why SGD is better. SGD with momentum is better than Adam. And if you read my comments also, Adam and others are generally used for lower training errors. They are going to give you low training error, by the way. Here is an exception. But if you use Adam and Adagrad and other guys, you're going to get low training errors. SGD is going to give you higher training error. But we're not interested in the higher or lower training error. We're interested in lower validation error. And at validation, these guys are never going to beat SGD with momentum. It is common to use SGD for all the sort of performances we are looking at. Adam and others are preferred for GAN and Q learning, which is reinforcement learning. And scientists are clueless why they are better for GANs and Q learning and VAEs also. But clear?
So is moving to these new types of gradient designs is reducing the overall computation time?
No, I'm going to explain that also. Now, HDD needs lesser memory since it only needs momentum. And please remember, we are calculating momentum value for theta, which means if I have 10 million thetas, I have 10 million momentums. Now, let's look at Adam, or let's look at something else. Let's look at Nesterov. In Nesterov, I need to calculate 10 million momentums and 10 million theta n plus 1s. And if I move to, let's say, Arasprov, I have to now calculate the momentum for the loss value also. So you're adding more complexity, right? So why I think HDD with momentum works is because it's simple. Because of the simplicity, there's some saving on the computation cost where we can maybe submit more variables there, right? But there is no clear answer why HDD is better than the other guy. So we are looking at a quantitative result right now, which supports HDD. Look at the last line, which is also very important. If your data is sparse, let's say you have 100 images per data set, per class, you are going to use Adam. You are not going to use HDD. HDD works when you have good enough data for the model to train on. But if your data is sparse, you're going to still get on Adam back. These are quantitative results, and these are important to know. Is the part clear? Okay, now let's go to learning rate, and we know about learning rate. If the learning rate is very high, we are going to go, high learning rate is going to be your light of speed. So when I click this button, we all are going to be, let's say, Bangalore airport. You know where we are? Russia. It's too fast for us to control. So your learning rate cannot be that fast. Now when I click, we are not going to move. See? It's so small learning rate that we have not moved. So we don't want that either. We want a learning rate which can actually take us in the right direction slowly. And we have to find that. Okay. Now, you've seen these images also. We want to move slowly in the right direction. We don't want to move fast, otherwise we are just going to go out of the value part. So we're going to skip that. Okay, now I'm going to cover one cycle policy and cyclic learning rate for you. We are not going to cover cyclic learning rate in a deeper manner. We are going to focus on one cycle policy, but both needs to be covered in parallel. Is the part clear? They're slightly tricky to understand, and that's why we are not going to cover both in depth. I'm only going to cover one cycle policy for you. Okay. Now, Leslie Smith is a great guy. He's some 70-odd-year-old person. He works in US Naval Defense, and he's writing these algorithms. Now, in the paper, he runs a range test. So what we are going to do now, okay, how do we train a network right now? We put our learning rate 0.01. We train a network end-to-end. That's what we are aware of. A model and everything else and image augmentation is already set, right? Now we are focusing on the learning rate part. We also know that as we are training further, our loss is reducing. I need to reduce my learning rate. One quick strategy for that would be reduce alarm plateau, which means if my loss looks like this, I'm going to reduce my learning rate, and it's going to look like this, and this is good. That is what we are trying to do right now, right? That is what we have done in the session code 7 and 8 of the second assignment also. But clear? So that all we are going to keep aside now. We are going to talk about, should we start at 0.01 or some better value? That's the discussion right now we are having. What is the one learning rate at which if I train my model, it can actually get the best start? All the other principles still stand. As I'm training, I have to reduce this value. But right now I'm interested in what should that start be. The part clear? Okay. Now I'm going to draw two graphs for you. Some time ago I told you your time of not just sitting and running a model is over. Now we have to actually put in hard work to find some values. So what we are doing right now is, I'm writing these as iterations. Also, we are not going to talk about epoch. Epoch is too big for us right now. One epoch, let's say I have 100,000 images, divided by 100 as a batch size. I have thousands iterations inside. I would have done 1,000 backpropagations. So one epoch is a big value for us right now. We are going to talk about iterations. How many iterations happen? I'm going to say this is 100 iteration, 200 iteration, 300, 400, 500, 600, 700. I am yet not finished with my one epoch. One epoch is 1000 iterations for me. Is that clear? We are also not training our model to begin with when I'm going to say we are going to do some update in a moment. Is that clear? 100% clear? Okay.
Iteration means that number of images.
Batch. 100 batches have been covered, 200 batches have been covered. Unless I cover 1000 batches, I have not covered one epoch. Okay.
So
now,
one iteration, one batch.
One iteration, one batch, backprop. One batch, backprop. Now, this axis is the learning rate axis, and this axis is the iteration axis. Right? I am going to pick some learning rates for me to test in some iterations, after some iterations. Right? I can't test every single learning rate. Right? I'm going to pick my own policy. Now, there can be multiple policies. I'm going to pick a linear policy, which means I'm going to pick this value and then this value and this value and then this and this and this and this. So I'm picking basically linear check. So I'm going to check here, I'm going to check here, 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 and here, and here. But here, it does not start at 0 for me. Let's say it starts at 0.01. So the 0th epoch, the first epoch starts at 0.01. This is what? 0.02, 0.03, 4, 5, 6, 7, 8, and so on. But clear? I have limited resources, so I can't check all the values. So I have to be slightly intelligent in how I do this particular part. Is that clear? Okay. Now, what we are going to do? This is our learning rate. I've swapped the axis, but this time this axis is going to be a loss value. Cool. Okay. Now, before we go there, I'm going to focus on one parameter right now. Let's say that parameter was 0.003, or because I'm playing in that value, let me make it 0.03. Yeah, 0.0321. That's the best value for that particular parameter we're talking about right now. But the network's initialized randomly, right? If it is initialized randomly, let's say I'm initialized at 0.01. It's cool? Okay. Now, if I pick my learning rate as 0.01, I'm going to check only for some time. I'm not going to keep on checking. If I check for 0.01, I'm going to go from 0.01 to 0.02. My loss is going to reduce slightly. Right? At this value, where I'm going to check, it may start at some random value, but the moment I check it for some initial value now, let's say I'm checking for 0.01, it is going. So this is LR equal to 0, LR equal to 0.1. If LR equal to 0, I'm reporting the actual loss which is there. That's the loss I had. And the moment I'm going to use a 0.01 update for this guy, my loss is going to slightly reduce. And that's the loss I'm reporting right now. Then I'm going to check for 0.02. So 0.02 gets added to this guy. Right? Now if I add 0.02, I immediately see that my loss is actually very small now, because I'm very close to the final value I want to be. But clear? Okay, now I'm going to add 0.03. If I add 0.03, this becomes actually 0.04. Now it's going to diverge. It's going to go up now. 0.0345 is going to keep on going up now. Is that clear? So now don't talk about this parameter. I just wanted to give you some background intuition of what we are trying to do. Now let's draw the actual curve you are going to find. This is the LR equal to 0, LR 0.1, 0.01, 0.02, and so on. Same values which we have picked here. You're going to get a graph which looks like this. Right? It is going to reduce because you're going bigger and bigger, and we're talking about average loss, right? We are going to talk about all the parameters. Right now we just saw one parameter, 0.03, that parameter is wanting to be at. But when you use a particular learning rate, we're talking about all the parameters. So on average, we're talking about what value should work for all the parameters in a better way. So you're going to test it for all of these values, and you're going to report the loss. This, by the way, is going to start at let's say 0.4. This will be 2.2 only. We have not finished even one epoch. Don't think we are training right now. We're doing backpropagation because if I don't do backpropagation, I cannot calculate the delta L for the new loss also. So I need to do the backprop. But I'm going to initialize my network and again start from scratch. Is the part clear? So for different learning rates, I'm trying to figure out what update on average works best for all the parameters I have. The update which works best for the parameters is going to take me to the ideal values they want to be at fast. The moment it happens, I'm going to see a bigger loss there, bigger reduction in the loss. That value here is called max LR. Is the part clear? That's the maximum LR with which we can train. Okay, now let's look at this graph. Now this is again iteration, same thing as we had, and this is learning rate, same thing we discussed. But this graph is actually changing exponentially. There is some change here, there is some change here. We can't see that. There's only very flat changes happening. But most of the change actually happens in this specific region. Now you can pick this also, where we're exponentially changing it. I request you don't do that. I request you to go for a linear change, right? A linear small gap of change. You're going to check your learning rate from 0 to let's say 4, right? And we are not running for full epoch training. We're talking about some iterations there. So each iteration you can also change, or wait for 10 iterations to change a particular value. Let's say I'm going to wait for 10 iterations, right? I would like to run at least 100 experiments in between. So 100 into 10 is 1000, which means I have to run my experiments 1000 times for 1000 batches. That is one epoch. So in one epoch, you're going to get these 100 points at which you're going to be reporting loss. That is going to give you, let's say, this kind of curve. Right? Now I know I'm somewhere here. I'm going to pick this range, and I'm going to pick this range, and I'm going to run my linear test again for this range, but now for 1000 steps again. So I can get a finer detail. Then I'll learn, okay, I'm going to test it for this guy. Then I'm going to learn, okay, this is where actually my loss is reducing even further. This part is clear. You have to do this manually several times to figure out what exactly should be a good learning rate. But is this part clear? Here, when you're seeing this exponential curve, you already have an intuition that you are going to be in somewhere in this range for your learning rate. We don't know that intuition if you are doing it for the first time. This is used by Jeremy Howard, who's running Fast AI. This linear curve is run by Leslie Smith, who actually wrote the algorithm. Is that clear? So instead of checking it exponentially, you're going to check it linearly. Okay, now let's go back. For this curve, or for the linear curve, you're going to get a graph like this. The graph we saw. On the bottom we have learning rate, that is how we are changing a learning rate, and on the y-axis we have a loss. For a specific learning rate, you're going to see that you have hit a very low value for the loss. Is this part clear? Okay. Now idea is to start small with a small learning rate. We are starting for 10 to minus 3, and we are increasing the learning rate after each mini batch till loss starts exploding. Once loss starts exploding, we stop the range test. There's no point testing after that. Plot the learning rate versus the plot test, which is on the bottom. Choose the learning rate one order lower than the learning rate where the loss is minimum. If the loss is 0.1, a good value to start is going to be 0.01. This is the value where the loss is still decreasing. Paper suggests that's going to be a good learning rate for the model. Okay. Now here, where the loss, plot the learning rate versus loss plot. Choose the learning rate one order lower than the learning rate where the loss is minimum. If this is where your loss is minimum, you're going to take a number which is 10 times lower than this particular value. This is the value where the loss is still decreasing, and let's say that's the value where the loss was still decreasing. So we are going to take that as the value to run our to run our model right now. Okay, is the part clear? Okay. So if you start there, let's say we got 0.1. If you do this, you're going to get 0.01. So you're going to start at 0.01 and then you're going to slowly reduce it. That still holds. But now this has told us the point where we should start. The good learning rate to start. That is not what we are interested in. Is that clear? We're not interested in that. That is one approach which you can use without using cyclic learning rate or one cycle policy. We are interested in cyclic learning rate and one cycle policy. It is related to what we want to do, but not really what exactly we want. We want 0.1 to be favorable for us, not 0.01. But clear? We're going to see what we are going to discuss now. Now, cyclic learning rate. The paper says that the cyclic learning rate between the lower bound and upper bound during the complete one run. Now, we are not going to go deeper than this. But what is going to happen is, you saw the 0.1 and you saw that 0.01. In cyclic learning rate, which we are not going to cover, okay, what did we learn right now? That we got 0.1 where the loss was lowest. We're going to divide this by 10, get 0.01 as a learning rate, and we're going to start from there and then reduce. That is what we learned right now. In cyclic learning rate, we're going to take 0.1 as an upper bound, we're going to take 0.01 as a lower bound, and we are going to shuffle our learning rate between that. Is the part clear? This is cyclic learning rate. This is something you need to know after the course ends. Probably you're going to be using this more, but we want to learn what is one cycle policy, right? And we want to look at one cycle policy because this is a new benchmark which is now the state of art competition for people. It's called Dawn Bench. This is handled by Stanford. You have you done your assignment 4?
Yes.
How much time you took?
2 days.
No, for one training.
50 of it is to 1 hour.
50 minutes.
50 minutes to 1 hour.
1 hour or something like that.
Yeah.
The state of art right now is 28 seconds.
They are using Tesla E4, right?
And paying 11 cents. That is why this benchmark is important. Otherwise, Google can take 400 V100s and train in 1 second also and create a world record. Then we people cannot use it. I will ask a very simple question. Do you think you can drive Ferrari today? Yes, on rent. Let's say Ferrari costs $4 million to buy, but what will be one day rent? 10,000? This is something we can afford. Let's say you will not, of course, but let's say you had to show it to someone. You can get a Ferrari for a day, 10,000 rupees, you can sit inside. Mercedes-Benz and all, they're already available as taxis for self-driving. They're 4,000 rupees per hour. You want to go to a marriage, get Mercedes, go there and then drop it back.
What is this cost for?
This is the cost of using the V100 GPU.
Okay.
So if you borrow, let's say 8 V100 Teslas, for 45 seconds, you're going to pay 11 cents. Less than 10 rupees. And if here the cost is not mentioned here, but this is also very, very low. So you are actually using, the state of art right now is 28 seconds. And you are using an hour right now. That's the aim. What we want to do is we want to learn how do we train model as fast as possible. And at a lower cost. So we can run more for experiments. Imagine that you have a client and client wants some demo to be done on Tuesday. One day you have to train the whole model. This is the approach we are going to take. And we cannot ask NVIDIA to give their complete server farm where we can actually run our models also. Right? That is why we are interested in this. So once you know this, you can expand it to some other domains also. Okay. Now, we are not going to cover the cyclic learning. Okay. Warm-up strategies. So this one thing which is not mentioned here, and that is annealing, which you are already aware of. Annealing is starting at 0.01 and then slowly dropping it. Right? And we have discussed we want to drop it because we want to go to a 0.03 and then 0.034 and 0.0345 and so on. We want to reduce we want to fix the least significant bits as we are training a model further. Right? But warm-up strategy is reverse of that. Warm-up strategy says that you are not going to start at 0.1. You are going to start at a small number. For small time. Not for long, but only for small duration. Now let's see why is that. Okay, SGD can tell you which direction you should move. Is it correct? Right? Okay. So you are here and you are using a very large learning rate. SGD told you to go in that direction. Right? You click the button and you have reached here. What if SGD was wrong? What if it felt like you have to go? We are calculating gradient, right? Gradient is that instantaneous gradient. So it was telling you that go straight, take a U-turn and come back. But because you have such a high learning rate, you just shoot across. You have missed that particular point. So we're going to start small. We're going to start slow. For small changes, we are going to allow SGD to figure out what exactly is the right direction I need to go. And then it's going to say, after those small changes, okay, this is exactly the direction we are interested in. So you're going to start small. This is very similar to how you do your gym also. Right? Or let's say you're in a hurry. Your aircraft is flying in 2 hours. You are in a hurry. Are you going to pick your key, throw on the door and then bang the door? You're still going to take your time. You're still in a hurry, but you're going to close the door properly and you're going to sit in a car. Will you bang your door? It is your car, you're not going to do that. Are you going to take out from your garage like a Need for Speed? Still going to take out slowly. Maybe there's an auto coming in. And then you're still going to drive slow. As soon as you hit outer ring road, you're going to speed across 80, 100, 120. But as the airport comes close, are you going to still drive at that speed? You're going to slow down. Right? Otherwise, those speed breakers are going to push you in air. And the moment you're going to slow down, the parking lot is there, again you're going to slow down and step out and then maybe run from there. So you're looking at the same stuff which happens for the gym, for the other things we also do, and same thing we want to do here also. We're going to start small. We're going to allow Google Map to tell us the go to right direction or left direction. So once, and that is what you also do, right? A turn is about to come and you're checking on Google Map is circling, you probably want to wait there to make sure that it's a U-turn, I still have to go straight. Same thing we are going to do here. We're going to warm, slowly increase and then slowly reduce. The part clear? So warm up is also required. So if you're going to pick a 0.01 as a learning rate, start small, go up and then go down. Leslie Smith just took this to his advantage and just kept going on and down. And there's something else happening here. This actually does something different. And we're going to discuss that particular part from a one cycle policy. Here, how many cycles can you see? 3. One cycle policy is this. We're going to start with a very small value. We're going to shoot to a very large value. Then we're going to drop down to a low value. Part clear? Okay.
How do you?
I'm going to explain. Now, what you're seeing right now is the blue one is a learning rate of 0.035 where we are starting it, and we are changing the values. When you see these changing graphs, that is where the loss is changing. The learning rate is changing, and we are changing by using reduce alarm plateau here. The moment you hit sort of plateau, it's not changing. You're going to drop your learning rate by 10 times, and then you're going to train again 10 times, and so on. There's something you are going to do. Are you going to also say after 40 pox drop by 10? After 40 pox drop by 10. So you can. This is again a step-wise reduction in your learning rate. But what you're seeing right now in the orange one is a cyclic learning rate. You just keep on shuffling up and down, and you'll see this juggle also, right? You can see this particular part where it's actually going through a nightmare. There's a hurricane which is in the model right now, and then it's actually going to arrive at a specific point at top. That is what is happening here, right? Okay. But we are interested in the one cycle policy, and both of them have a very similar result. And I'm going to use a very beautiful image, not designed for this purpose. Alright, now that is where our weights want to be at. That is where our weights want to be at, right? And I'm going to talk about only one particular weight, and that weight happens to be this guy. Right? Okay, this guy. Okay, and this guy actually wants to go here. Right? That guy actually wants to go there. Right? These are randomly initialized variables. It can be in separate directions also. Now, if I don't start slow, what is going to happen? SGD is going to realize that if I start fast, basically, if I start very fast, I may actually go in a direction, and then SD will take a long time to push me from some boundary to finally arrive at this particular point. Is this point clear? So we don't want that. We don't want to start fast. We want to start slow, so my SD can figure out what direction should I actually take. Now, if I get stuck here, these are minimas for me, right? If I get stuck here, how will I come out? I need a push, right? Momentum we're already using. So the only push left for me is learning rate. If after given a big learning rate, even after I'm given a big learning rate, if I give a big learning rate to this guy, it is going to jump out. If I give a big learning rate to this guy, it's just going to shuffle inside. That is the shuffle you're seeing. Even after giving a big learning rate to all the parameters in my network is not moving out. That is a guarantee that most of them are actually in the value they want to be. After that, I have to slow down to make sure that they actually arrive at a spinal point. Right? So when you shuffle it out, when you shake the network hard, when you're going to give a very huge learning rate to this guy who is stuck here, it's going to come out automatically. It's going to go there again. But because the learning rate is so large, it's just keep on shuffling. But the moment it reaches here, it is going to be in such a valley. And now, because of small learning rate, it's going to take some time and finally reach at this particular point. Is the part clear? So that is what one cycle policy is. We are going to increase it slowly, and we are going to shake it with a very large value, and then we are going to slowly reduce it and push it to final value. That's the kind of arrangement we are interested in. Okay, now this is one video I'll recommend you go back and look at it. Now, there's an original implementation and there's an implementation which we are going to implement. We are going to discuss both the things. Now, author recommended that we do one cycle policy in 2 steps of equal length. This length is not equal for us when we are going to implement, but this is what the author started with. We choose the maximum learning rate using the range test. Remember, we got the maximum there as 0.1. That's the maximum we're going to use. We are going to choose the lower rate as 1.5 or 1 by 10. You see this OR? That OR basically means a grid search. You have to find out which one are you going to use. So right now I only know 0.1 number. I don't know what this number is going to be, 1 by 5 or 1 divided by 10. We go from the lower learning rate to the higher learning rate range in one step and back to the lower learning rate in step 2. We are not going to do that. We are going to start from a lower number to higher number. We are going to go from higher number to a lower number and from lower number to an even lower number. So for us, it's going to be 3 steps in that one cycle policy. We pick the cycle length slightly lesser than the total number of epochs to be trained. In the last remaining iteration, we annihilate the learning rate below the learning rate to go to 110 or 100. Same stuff which we said. So the second one is not going to be equal in length, it's going to be slightly shorter. And from there, we are going to go even deeper. Okay. Now, what is written is this. I'm going to take this of equal length. So this is, let's say, 14 epochs for me. This is also going to be 14 epochs. I'm going to start small and I'm going to reach this point. This point I know is 0.1 from my range test. This point may be 0.2, this is divided by 10 or divided by 5, or maybe 0.1. So I need to figure out what is this going to be.
0.02.
Right? So I'm going to be either of these points, but I have to figure out which point it is right now. But let's say we are picking this just for discussion. I'm going to go on top, and in 14 epochs, at around 12th epoch, I would have reached this point at 0.02, and then for the rest of the 2 epochs, I'm going to further reduce it to 0.02. Remember, we are doing iteration wise change here. We're not doing epoch wise. Otherwise, I'm going to go from 0.02, then divide a big range there. We're not interested in that. We're going to go slow. So every iteration, the learning rate is going to change, not every epoch. Is that clear? This is what we discuss as written in the notes.
So
what
if we reduce to 0.002, then loss will be more, right? That's what that graph.
No, if in fact this loss is going to be much higher here. You see that curve?
That's what I'm saying. Loss will be.
You see that curve? It's peaking up as we are actually doing the last leg. Because now you're fixing, now you're doing those minute finite changes. You're already at 0.0346, but you should be at 0.043459 something. So I get to fix those small numbers. This is what we discussed, but actually what people use is this. I'm going to figure out how many epochs I have to run. How do I know that this is 24 epochs? We are going to discuss in a moment. This is going to be our peak line, which is going to be some section which is before the midway of the 14th. This is 12. We are before the 12th epoch. I'm going to start from same number 0.2 or 0.2. Or 0.02. I need to find out which number this is. This is 0.1 for me, right? And then we're going to hit it here, and from there I'm going to drop further. Right? This is same number as this guy. Let's say this is 0.01. This is also going to be 0.01, and this guy is going to be 0.001. 10 times lower than that, or 100 times also. It completely depends, but we have to find out. Is it clear? So in this graph, what all do I know? I know this. I don't know this. This is very important for me. Right? Now, how are you going to pick this? You're going to go on Dawn benchmark, and you're going to see that, okay, this guy is using 28 seconds. You want to break this record. You have to have some sort of ambition for this thing to work for you. So you are going to say that I want to train my network in 27 epochs or 26 epochs. Let's pick 26 epochs. Alternate example would be that you have only 100 seconds to train a particular model. This CIFAR 100 seconds will make sense for it. When you go to ImageNet, it's going to be in hours. ImageNet otherwise take days to train. From days, you're going to rush it to hours. So you're going to say, I'm going to borrow my V100 only for one day. That is the amount of money your boss has given to you. One day V100 is still going to be running in thousands. We are talking about seconds here, and now we're just converting into an hour. I have only 1 hour to run. But let's say I'm going to borrow my V100 for 1 hour. Okay. Now, if I had borrowed my V100 for 1 hour, I would have paid not mentioned here. If I borrow x3 large, is anyone mentioning? Okay, we'll scale up from here then. V100, if I run for 1 minute, I'm paying 2 cents. I'm only using one V100 here. So this is what? Into 60 here. That is going to be $1. $1? Close to $1. Still cheap. Well, let's say that's the amount of money you want to spend today. Right? One V100 for $1, $10, whatever the number is. That's the budget we have. Okay. So you are going to go on V100. You're going to run your model once. Okay, you're going to run once, and that is going to help you understand how much longer your one epoch is going to run. I'm trying to figure out how long one epoch takes. One epoch takes, let's say, 1 minute for me. Right? That means I can run for 60 epochs. But that gives us this number. If one epoch takes 2 minutes, then I can run only for 30 epochs. Then this 24 is going to be 30 for me. If I'm targeting, let's say this competition, in this competition 28 seconds is the record, I'm targeting 26 seconds. And on V100, let's say it takes 1 second per epoch for CIFAR 10. Then I'm going to use it for 24 seconds. And that, because my target is 26 seconds, my epoch is going to be 26. Is part clear? That's how we reverse calculate. For image and all, and for when you're doing for office, you can be lenient. You can say I need more. But when you're doing this kind of competition, you have to reverse calculate. So that gives me, let's say, a number which is 26. Not 24, but 26. So I have 26 epochs in which I'm going to finish all of this. Clear? Okay. Now we need to find this number and we need to find this number. Both the number. Are we going to go for 0.01 or are we going to go for 0.02? We can't keep everything variable. We have to fix some things and then we have to go back. So first thing is that you're going to fix this number in your mind. I'm going to say I'm going to use a 0.02 number to begin with. Okay. Now I'm going to run from 0.02 to 0.01. This number is less than half, so this number is less than 13. I'm going to run from 0.02 to 0.1 multiple times. Right? I'm going to run this in 7 epochs. I'm going to change from 0.02 to 0.1 in total 8 epochs. I'm going to run for 9 and 10 and then 11 and then 12 maybe. Right? It's always going to be less than the overall number. The part clear? What we are doing is we have just run 1, 2, 3, 4, 5 experiments, 6 experiments. Okay. Now this is the accuracy or the loss curve. We are interested in loss actually. Right? This is the loss value. And these are the different tests I ran for. Now, when I ran for seven epochs, right? When I ran for 7 epochs, I'm going to get this line, right? When I ran for 8 epochs, I'm going to get, let's say, this line. When I ran for 9 epochs, let's say I got this line. Lower loss is good thing for me. When I ran for 10 epochs, I got this line. I ran for 11 epochs, I got this line, and 12 epochs, I got this line. Right? Now this is clear that I need to pick this as my epoch, because at that epoch it was lowest. Right? So we have run already many experiments. To finally be able to run a model in 26 seconds, I would have wasted already hours there. Usain Bolt can run in 10 seconds 100 meters after spending years of training. You see the dilemma here? But once everything is ready, you can run it for 10 seconds or 25 seconds as many times as you want. But initial grid search is going to take a lot of time. That is the time we are spending right now. There's another way of thinking about it right now. For each learning rate, you are able to decide how far you are going to go. You want to go as far as possible. But if you go flatter, you are going to go shorter. If you go wider, you might actually land wider. But if you go like that, you might actually reduce your projections also. We are trying to figure out the accurate angle at which I can drive fastest. At what learning rate I can actually arrive at the best loss value. Okay, now that is going to give us this point. Correct? Now, if you are interested, you are going to fix this point, which is what? Epoch number 7 for me, at which I need to be at 0.1, and then you're going to check these values. You're going to check it for 0.01, 0.02, 0.00, 0.015, 0.016, and so on. If you want to do. Otherwise, you can be stay happy with this. Is that clear? Now, the moment I figure out I'm going to use a 7th epoch and I don't want to test this out, I can actually use that as a checkpoint. I can actually save that model, right? Now, after saving that model, let's say we have saved that model, which means I started at 0.2 and in 7 epochs I reached at 0.1, 0.02 and 0.1, and at that point I was, let's say, around 70% accuracy. Okay, how many epochs I have? 26. Out of 26 I have already consumed 7 epochs here. Okay, now this is the next leg. You have to figure out what is this point now, right? And overall how many epochs are left? 21 epochs, 19 epochs, sorry. Overall 19 epochs are left. So you're going to test this value to be at 15, 16, 17, 18 and maybe 14 also. One of the values is going to click for you. Whatever value clicks for you is save that particular model, right? Because we are trying to still and run. And if I use 16, how many epochs are left? 3 epochs. In 3 epochs you're going to go from this to the other low value you are interested in. After you find all the value, your code is going to look something like this. Right? After you find all of these values, your code is going to look like this. Here I am importing all the important family members of this code. Okay. We are running in an eager mode right now. If you don't know about that, then it's fine. The code is actually taken from this. I've modified the code slightly. This is where we are doing some PyTorch initialization. I request you to go through the code and look at this particular block. We are going to only cover the part we are interested in. This is how we define our models these days. This is how TensorFlow 2.0 model is also written as. We are still using TensorFlow 1.0 here, but this is how we are writing our models these days. I'm interested in showing you this line, which says lrschedule is a lambda function of an interpolation function from 0 to interpolation function going from epochs plus 1 divided by 5, the same thing which we saw, going to the epochs, right? So this is a range which we are looking at, and it's actually going from a 0 learning rate. You get this point? These are 3 ranges I have. This is 0, this is 7, and this is 24 for me. This is 0, this is learning rate, and this is 0 for me, right? 0, learning rate, and 0. And this is 0, epoch divided by 5, epoch plus 1 divided by 5, that number, and then. So we are defining the 2 sides of a triangle basically. This is what you have to fix after getting that test. So you are going to say that at 0 and at the 7th epoch, we are at 0, and here we are at 0.1, here we are at 0.01, here we are at 0.1. Then you're going to say comma, then you're going to say after 16 epochs. So 7 plus 16 is 23. So you're going to write 23, I want to be at 0.1, and then you're going to write the last number as epochs, which is 27. There I want to be at 0.02. That's the interpolation function which you were just in one line writing. Now once you write that, I'm going to do some image augmentation on my data set. Right now I'm taking my image X, right? Let's first see what is X. X is a padded image where I'm taking my X and I'm padding it by 4 pixels on all the sides. I told you in the last session. We're going to take our image, pad by 4 pixels, and then we're going to do what? A random crop of 32 cross 32 cross 3 out of that. That gives me a random displays object size. That I'm going to do a random flip. Ideally, I should have done cutout also after this, which is not done in this example. Is that clear? Okay. Now, if I do all of that and if I run my test now, that is what I'm going to get. Look at the first epoch, 54 seconds, and each epoch is taking somewhere around 37 seconds for me. And by the time I hit my 24 epochs, we are at 93% accuracy. I've taken 700 seconds on Colab. This is already a 1/6 or 1/7 time less than what you are spending as of now. Is that clear? Now, if you want to take this number to 94, which is the competition target, what all is required? We need V100. On Colab, I can't do anything to reach at 26-27 seconds. I need to add weight decay. Without weight decay, okay. Why do we need to add weight decay? I've used a dropout already here. You see the code. Here I used dropout. Right? Image augmentation most I've used. So cutout is left. So I can add some sort of cutout. But look at my log. The original code, by the way, is at 92%. Just adding dropout is taking it to 93%. But I'm also seeing this as 99%. Right? And I need to be at 94%. So there's one person left there, there's one person left here. Unfortunately, I don't have extra epochs. If I had extra epoch, I can still test whether at 100% what is the number I can hit, but I don't have extra epoch. So I have to do fast regularization in these epochs only, which means whatever I have done must remain there, and I need to add something more there. So what I need to add is weight decay. Weight decay is something which is further going to help us reduce that overfitting initially in the overall part of the network. I also need to add cutout data augmentation strategy. I need to save my images as TF record. If I want to reduce time, you cannot be reading images from your disk, right? How do we run our model? Your CPU wakes up suddenly, you have run a compile code. Your CPU wakes up and sees what is the first line. Oh, go and read 512 images from your hard disk. It goes to the hard disk, asks the hard disk guy that can you give me 512 images? It takes 512 images, then read the second line, do a random pad. So it's going to do a random pad on all of this happening on the CPU, by the way. I'm going to do a random pad. Then it's going to do the next line, now do a crop of 32 to 32. It's going to do a crop of 32 to 32. Then you're going to say, do a flip. Then it's going to do a flip. CPU, it runs serially. Then you're going to say, do a cutout. Cutout is also done. Now you're going to say, batch it together and give it to GPU. So CPU is going to batch it together and give it to the GPU. What is GPU going to do? Done. Next batch. Which is hold on. What is the first line? Go and pick the 512 images. You're going to pick 512 images. Then what is the second line? Do a pad of 4x4. So you're spending most of the time on your CPU where GPU is sitting idle. We don't want that. So if you look at the code has some lines which you should be interested in as you learn this further. It says something called prefetch. It says fetch the next batch for me now. So it is asking the CPU while I'm doing my work, why don't you get the batch ready? So you're not going to waste cycles on the CPU. What we are also doing is, maybe not in this specific code, but let me just check. Yeah, we are not doing it here. First of all, eager mode allows me to make sure that I can run my epochs like a for loop. Otherwise, it is not in your control. If you want to write a scheduler for your Keras, it just says model.fit. Inside, you can't do anything. You just do model.fit, right? There's nothing else we can do. But if I use eager mode, the whole code works like Python. Actually, I can stop after some batch. Imagine that you can actually stop mid in the epoch and then start again. So eager mode is allowing us to do all of that. Now, what I have not done right now in this code, or what is not done in the code right now, is that we are reading directly the CIFAR values. What we should do is to convert that to TF record. TF record is a tensor directly. It's stored as a tensor directly, which can directly be streamed to a GPU. It's a direct vector which can be read, and it does not have to decode it. Otherwise, your images are stored as JPEG compressed format. I have to decompress it and then store it back to my image, and it's going to expand big. Right? The amount of bitmaps we use is huge. For example, if I take a screenshot of my screen right now, and if I save it as a bitmap, right? I'm going to, let's say, on my desktop, and I take my screenshot again. But this time, if I save my image as PNG, then I save. Yes, overwrite that. And if I look at my desktop, okay, those are two images we stored. The PNG image is 329 KB. Windows is not really a good operating system for saving these screenshots. It already expands a lot. Bitmap is 19 MB. Right? Bitmap takes a lot of space because every pixel is stored as is. It's not compressed. Can go to 123 also, right? So these are compressed formats, but when you actually upload to your GPU, it has to expand as a normal bitmap value, and that part is going to be pre-done. So we do it, and then we process also on the GPU. Now this is your assignment. Implement the code shared with you again. This is the code I'm sharing with you. This code, by the way, it says 0 points and it says exercise. It is good to know how to do this, but this is not going to be a qualifier. This is a very hard assignment, and this was given to EVA batches also, and most of the people get depressed after doing this assignment. I don't want to give you this assignment as this problem as an assignment. So good to know and good to have, good to solve. Implement the code shared with you again, but this time add cutout to the implementation. What you are going to do is to first of all understand. It's very important that you understand this code, and you're going to change the image augmentation in such a way that you're going to say this X, crop your image which is X by 32, 32, 3. Do a random flip of whatever output you're going to get from this, and you're going to say TF dot cutout or your own model, cut out this image with a section of 16 cross 16 or 8 cross 8. That's the only logic you need to add. Achieve 93.5% or more in 24 epochs. You have to just increase by 0.5. And believe me, it's going to be so hard for you that you're going to just keep on scratching your head. What should I do? Right? Let's say we are given a Ferrari, not even a Ferrari, F1 racing car today. Does not matter how many weeks we try, we are never going to be able to match the speed of the racers who actually do. And the code is actually taken from such a racer. These guys know what they are doing and exactly what needs to be done. For you to arrive at that level, you have to spend a lot of time. Best thing we can do is to analyze the code. I will request you to go to this particular blog, right? This code is here, and this code is taken from this blog. Go in that blog and try and understand every single line. Why the hell are we initializing our network in a PyTorch fashion? We are not inputting any PyTorch anywhere. It is just called init PyTorch because it wants to tell you that he's using the PyTorch way of initializing parameters. What is PyTorch way of initializing parameter? It's a Kiaming He starter policy. Why are we using Kiaming He? Then more questions. So one session for us. We can't go inside that particular part. In Keras, we don't have Kiaming He. So we have to write manually the way we are going to initialize. This is the manual function for that initialization. Otherwise, you can use Chlorod and Xavier, which is available in Keras. Now we are writing a convolution like this. We are defining a function, and then we are going to call that function, right? And then we are using ResNet. This is a ResNet block. In ResNet block, we are sending something called pool. We don't know what pool is right now, but we are also sending this variable res, which is a boolean variable, either true or false. When I actually use res, I'm going to be keeping my skip connections. If I'm not sending any res, I'm not making a skip connection. Now let's understand the model. I initialize my model, self init con bn. Okay, so the first time I'm calling this code, res con bn. What is con bn? This is the code which is coming in, which means this is the first layer which I've just made. I made a layer with followed by dropout, followed by batch transformation, followed by reload. Right? That's the code for this line. Then I'm calling my ResNet block. This is a ResNet block which is there. I'm calling my ResNet block with C into 2, which is 64 into 128 parameters, with max pooling layer. What is pool? Pool is equals to max pooling. So I'm sending a function inside, which gets converted into max pooling and comes back. I'm saying I need a skip connection there. Then for the second block, I'm sending a max pooling layer, but I don't want a skip connection there. Why have we not taken a skip connection? Right? Then third one, I need a skip connection back. Then we are adding a global max pooling, not global average pooling. Global max pooling, right? And after that, there's a dense layer connection, and then finally we are using this. So there are many things which you need to read the code and find out why that has been done, and that all is going to be explained in this blog, which refers to its old blog, which refers to some other blogs on the outside periphery. So it's like a Wikipedia. The moment you click it, your whole day is going to be gone. But it's a very important exercise if you really want to proceed forward, because that's the right way to understand how to learn the right things. You need to know how TF record works, you need to know how to attain fast, you need to know why initialization matters, because the rest is already done with you. It's all about exercise now. Now let's come to an actual assignment, right? I wish I could have given you this as an assignment. I would have been very happy, but this would have broken you. You would have needed literally 7 days of time to just figure out the whole scheme of things here, and code is also complicated. Okay, the actual assignment. Once Monday people submit their annotation files, I'm hoping you're submitting it already or you're annotating it already. You just make sure that you're clicking save also, while in between some people are reporting that after doing whole annotation when they click save it's not helping. Okay, I will combine the files and share it back with you on Tuesday. Right, I'm going to upload it somewhere and you're going to use that link to download in your code, and you can directly process that. Now if you've already started annotating your files, you know the images are not 200 cross 200 in size. They're of different sizes. So the image I'm going to share back with you is going to be all scaled down to 200 cross 200, so we can use Colab to train, and it's going to be padded with 200 200. So we are still going to be working with a square image, not rectangular images. We want to make sure that happens. Okay. You are implementing a multi-class classification, which means in one image you're going to identify whether you have a cat. I was about to say cat dog. Whether you have a person who is very healthy, He's carrying a bag. What is his emotion? I'm just going to show you the code. This is how the code looks like right now. And this code is hosted at that link. So when you click on this link, this is going to open up. Cool. I'm going to run it with you. So I've saved, I've annotated 100 files myself, and this is stored on my Google Drive. If you want to use something from your Google Drive, this is how you use, right? You upload a folder to your Google Drive called person dataset. That's the file I have. Okay, I can. Why do I skip this? Okay. It's already mounted. It says the samples are already there, so I don't have to unzip. So I'll not run that command, but if you do it for the first time, you have to run that command. That's a simple code which is calling all the gods. Then I have this folder already. One is called via.export.json. That's a JSON file which you are making individually. I'll have to combine all the JSON files and share back with you. And images are stored in an image SA folder, which is here. These are the 100 images, but when you are going to look at it, based on how many of you have done the assignment, you're going to get 20,000 or 27,000. If everyone has done, 27,000. If less people have done, 20,000. People who are not doing assignment 4A will not be able to do assignment 5. So there's already first clear cutoff there. Now, right now we are looking at annotation list. Okay, df head. All of this is something you need to know. Right now you're looking at a sample of your data. That's a sample which I created. But after I combine all of your annotation, we are going to look at it. Image A, 55 years plus, slightly overweight, female, middle class, educated, daily office bag, other jewelry true. Other jewelry is bangles and let's say chains if you see there. Some other accessories you're seeing. Clothing style average, emotion neutral, clothing style daily, and body poses frontish. That gives us my analysis of my data, like how many tags are actually done properly, or how many tags are done, statistics of the tags of my data set. Okay, I'm going to quickly jump to the main code. Here I'm resizing and padding, but the final images you are going to get are all going to be 200 cross 200, so you will not have to run. So I will refresh the code and share with you. We are reading the image. I'm seeing what my image number 10 looks like. It says 210, age is 25 to 35, slightly overweight. These are statistics of that particular image. Let's see that image. When if you're trying to run OpenCV and you're trying to run IAMShow, it would not run unless you call this guy patch with the patch, this patch, google.colab.patch and import CV. Then you can run OpenCV, some of the OpenCV code, IAMShow code. Okay, it's done. Okay, you're not going to do all the classes. As the data comes in, maybe I'll add more classes. Right now, from that data set which you have made, you're doing gender, image quality, age, weight, bag, pose, footwear, and emotions. So these are 8 classes which you're going to be doing. If I see the data quality is good for other classes also, I'll include them as well. So I just define that, and right now I'm defining my X-train, Y-train, same thing as we do. Okay, I'm using a VGG backbone here because I want to see how the model works. You are going to be writing your model. This is not a transfer learning exercise for you. I'm allowed to do it. You are not allowed to do it, right? I'm using transfer learning here just to see that data can be trained or not. Okay, I'm using a VGG backbone, and this is where we're downloading the weights. Right? You are making this guy backbone. You're basically making a whole model end to end, and then you're going to be using this code to link your model to train it. Okay, this is done. df.describe. These are the same data sets we looked at, perfectly fine. I'm going to freeze my backbone. I don't want to train it, so I'm not training the complete VGG. I've just added some layers. I want to train those layers. I'm using HGD learning rate 0.01, momentum 0.9, compile categorical cross entropy. I've compiled my model, and now I'm going to run. Now, because my data set is small, it's going to take around 10 seconds per epoch, I believe. One second per epoch. It's a small data set, only 100 images. But when I'm going to give it to you, you're going to take longer time on that. And does not scale with images. If 10 images take 1 second, that doesn't mean 20 images are going to take 2 seconds. It's a GPU. It loves parallelism. Right? Now let's look at the accuracy which this model has received. Right? So we have 8 accuracies, 8 validation losses, 8 loss values, 8 training accuracy losses. So there's a huge log you're seeing. Emotion, we are already at 88% for this data set. A small data set, so misleading already. Footwear, 56%. Then bag is 36%. We are doing bad there. And I think we had 4 bags or 3 bags. How many bags we had? 4. Then 36. It means some training is happening. Otherwise, it would be 25%. Right? And age 46, 44%. Not doing good there. Gender output 60%. Barely there. Male, female. Others, I don't think anyone has clicked. But we still have 3 classes. From 3 classes, 60% is still a good number. But this is again 100 images, so we cannot rely on that. Is the part clear? So what you will be doing, you'll be submitting this log essentially, your model and your code. So this is a temporary file for you to see how you're going to make changes to it. You can start working on it already. You can replace the model with something of your own model. You have to figure out. So final image I've already told you is going to be 200 cross 200 size. So you need to figure out which model are you going to run. Okay, you can run your model as long as you want. No restriction. You can use any model of your choice. You can use ResNet, you can use DenseNet, you can use any model. You want to use fully connected layer also after listening from me that we should not use it, use it. Anything you want, right? So you cannot ask any question, can I use that? Can I use ResNet 18 and change something to make it ResNet 20? You're free to do anything you want, except transfer learning. Transfer learning you cannot do. You can use any augmentations of your choice, right? Since this is a blind assignment, which means I do not know what is going to be the highest accuracy target, you guys are going to decide that. So either you kill the person who's going to get the highest accuracy and beat all of you, or you all have to keep on training a model till you believe that you are going to match his accuracy. What I'll request you is to be communicative on the Telegram, right? This is not going to be on your period. The moment you tell someone that I'm hitting this 68% accuracy, you're not going to suddenly make other people get that accuracy, but they will get some idea of where the whole batch is moving, right? Start sharing your numbers. And that is what is going to make your group different from the other groups. Other groups don't talk to each other, and they're not with us. I want you guys to talk to each other. There's already very healthy communication on Telegram. If you make it better, people are going to learn further from you. So share your numbers, that is good. Marks will be allocated percentile wise, right? And this is going to be getting added to the overall assignment. So I'm going to talk about that. Submit your GitHub link with the project 5. This assignment cannot be submitted as a group. So if you're working in a group, it's time to separate now and to do the individual assignments. Otherwise, you have 4 people in a group, only one is working, the 3 gets the benefit, and that kicks other 3 people out who actually did the assignment and should have been in the benchmark list also. Right? So this is an individual assignment. Deadline is 22 December for all the batches. Right? Wednesday batch is going to be at a loss because they're the last batch which is going to get to know about the deadline. But believe me, they're not at loss. We all are lazy. Because this is 22 December, you're going to say today is what? 5th, 6th, 7th, 8th, 9th. So it does not matter. Right? And I've intentionally given enough gap so you can actually process the data and start working on it. Believe me, your 7 days are required for this assignment. There's a lot of small stuff you have to do, and people are going to update you in the end, right? They're at the end last week, you're going to tell that that's the accuracy you're at. Then you're going to go and look at your model and then you're going to update it back. Don't do that. Try to put as much time as required now. Do the best things possible, get your model correct. Look at the models, you can copy VGG also, you can copy ResNet also, completely fine. But I'm fine with you using any model. If you want to not train on Collab, completely fine. You can buy a V100 or you can buy a desktop or you can train on your laptop also. Submission has to be an EIP4 file, a notebook file which I can review for the logs. But here, the completely open assignment.
What is the final accuracy if you have 8?
I have 8 classes, so I'm going to look at, so it's a percentile. How do you do percentile?
Max random.
Max among each of the class, and then based on that, where exactly your accuracy is. And generally is going to be similar for all. If you're doing very well on age, you're going to be doing very well on the, because most probably you're not going to be writing a different way of, you're not going to write a multi-objective loss function. That is what I've already given you. I'm saying that you're not going to play around with the loss function. If you can, then you can basically change the values as well. Change the values of your accuracy for a particular loss.
Just to clarify, when you say you can't use transfer, you can take a ResNet
You can take a resonant model and modify it and initialize it from a random value and then train it. Pick anything, you have to initialize it with the random values and then train it. I'm going to look at the initialization code, that what exactly are you using for the initialization code.
In our earlier codes, one function is there, schedule. So there, how you were defining it?
Grid search, same thing I explained today. You have to test it multiple times to arrive at a final value.
Now that we know this one, but before that, how was it?
Test out different values. So what I'm doing there is I'm reducing LR as after some epochs. You have to test it manually. So your hunch is going to say after change after 10 epochs, then you're going to know maybe 10 is not fine. I'm going to change after 5 epochs. So those are hyperparameter you have to test on.
Not that one. There are two ways, right? One is like the last assignment which we have done, like for.
You're talking about the code 7, right?
Huh?
Code 7. Assignment to code 7. Assignment 4B.
4B, whatever we have done now.
Uh-huh.
So, in earlier codes, yeah, 27, there this elapsed function was like, it was defined.
Yes.
Some number plus that number of epochs into again 0.0312, something like that. So, how it was arriving at that one?
We have not arrived, we have searched for it. Those values are changed. First change every epoch, then change after half the epoch, then change after only 1/3 of the epoch.
Yeah, that is fine. Like when we are doing that if clause, like if the epoch number is greater than or lesser than, then we are taking that. That is one way. The other way is where that function is itself
No. Okay.
defined.
Yeah.
One or two of the codes.
This function number 1, which says change the LR after every epoch. This function number 2, which says change the LR after every epoch plus 1/2. The third function which says that okay, change the LR after every epoch plus 1 into 0.32. There's some number like that. So you have to find that number.
Okay,
After
that is one I was.
Yes, you have to find that number. So you're going to repeat this experiment multiple times.
And one more thing for start out, when he was trying to import that package of random erasure, it was not, then we have to define the function in the code.
After defining it worked?
But
Maybe some version error.
Version.
Maybe some version error. Now, in fact, from now on to next 6 months, you're going to suffer a lot of problems.
Because of Python 3?
Because the Python 3 has already changed. Now, 2 is already obsolete. Most of the code is on 3. And TensorFlow is also moving for TensorFlow 2. So, in some months, it's going to stop supporting TensorFlow 1 altogether on Colab. Then we are going to face some issue. So, that's why. And that should not happen before 22nd of December for you.
So every time it pops up actually that warning that upgrade the TensorFlow.
Yeah, we're going to ignore that. Hopefully by 22nd December, till 22nd December, it's not going to be there. What is the warning showing me? We'll soon switch. So it's soon, so we don't know when, but let's hope it's not 22. Cool. Okay, now I can stop recording.